How did everything begin from nothing? This is not only a question of science, but a profound mystery that touches philosophy, existence, and the very fabric of reality. From the birth of particles to the formation of galaxies, the idea of creation from nothing challenges everything we know. To explore it, we turn to particle physics and cosmology, fields that study the smallest building blocks of matter and the grandest scales of the universe. Together, they reveal how space, time, and energy emerge from an unseen void, giving rise to stars, planets, and eventually life itself. Along this journey, we'll dive into quantum mechanics, the Big Bang, dark matter, dark energy, and the elusive dream of a theory of everything. Join us as we trace the story of how nothing became everything. Don't forget to like, share, and subscribe to follow the chapters of this cosmic journey. Imagine pressing rewind on the universe. Galaxies shrink, stars collapse inward, planets dissolve, and even atoms themselves break apart. If we could keep reversing time, every particle, every flicker of light would collapse back into a single, unimaginable point. And then beyond that point, what would we find? Absolute nothingness. But here lies the paradox. How could everything we see around us, from swirling galaxies to the beating of a human heart, have emerged from nothing? This question is not only scientific, it is one of the deepest mysteries ever asked. Philosophers, theologians, and scientists have all tried to answer it in their own ways. Can something truly come from nothing, or is nothing itself an illusion, a concept that cannot exist in reality? When we think of nothing, we imagine emptiness. No space, no time, no matter, no energy, a complete void. But modern physics complicates this picture. What appears to be empty space is never truly empty. Even in the deepest vacuum, particles constantly flicker into and out of existence in fractions of a second. These fleeting appearances are called quantum fluctuations. They hint that the very fabric of reality may never be perfectly still, that even nothing is alive with hidden energy. So what do we mean by nothing? To a philosopher, it is the absence of being itself. To a physicist, it might be the lowest possible state of energy, a background field seething with potential. These definitions don't match, but they reveal the heart of the problem. Perhaps nothing, as we imagine it, is not real. This mystery is not new. Ancient thinkers wrestled with it thousands of years ago. In Greece, the philosopher Parmenides insisted that nothing could not exist at all, because even to speak of it gave it some kind of existence. To him, the universe must be eternal, without beginning or end. Other traditions told different stories. In Hindu thought, the universe rises and falls in endless cycles, emerging from a vast cosmic ocean. In Christian theology, creation is described as a rising out of nothing by divine will. These ideas may seem distant from modern science, yet they reveal how human beings across time have struggled with the same paradox. Is nothingness an illusion, or is it truly the starting point of everything? Science approaches the question differently. It looks not for myths, but for evidence. The Big Bang Theory tells us that the universe began about 13.8 billion years ago in a state of unimaginable heat and density. Space itself expanded, carrying matter and energy with it. But this description begins after the universe already existed. What about before? What set it into motion? Did it emerge from nothing or from something we don't yet understand? Right now, physics has no final answer. Einstein's theory of relativity, which describes space and time, collapses when pushed back to the very first instant. Quantum mechanics, which governs the smallest particles, also fails to fully explain the origin. The very moment of creation lies at the boundary of our knowledge, where the laws of physics themselves seem to break down. Yet some clues emerge. Quantum mechanics suggests that nothing may not be stable. In the vacuum of space, pairs of particles and their opposites, called antiparticles, are constantly appearing and disappearing. Normally, they cancel each other out so quickly that we never notice. But under extreme conditions, such as those that may have existed at the dawn of time, one of these fleeting fluctuations could have sparked a new universe. Some physicists even propose that our cosmos began this way, as a tiny quantum fluctuation that expanded into everything we see today. This is a staggering idea, that the universe itself might be the product of nothing ref. Using to stay nothing, it blurs the line between emptiness and existence. The void is no longer a dead absence, it becomes a restless field of possibility. And this question is not just about physics, it strikes at the heart of what it means to exist. If the universe can spring into being without cause, then the fact that there is something rather than nothing becomes both unsettling and awe-inspiring. We look up at the stars and wonder why we are here, but perhaps existence itself is simply inevitable, born out of the restless potential of nothingness. As we begin this journey, we stand before a paradox. Nothingness may not exist in the way we imagine it. The emptiest void may still hum with unseen energy. The first flicker of the cosmos may not have been a creation in the traditional sense, but a transformation, a quantum shift from emptiness to being. This is where our story begins. In the chapters ahead, we will explore how physics, cosmology, and quantum theory attempt to unravel this mystery. We will meet the particles and forces that shape reality, and we will travel back to the first moments after the Big Bang to see how the universe blossomed from apparent nothingness. The journey from nothing to everything has only just begun. When we think of reality, we imagine solid objects, the ground beneath our feet, the walls of our homes, the stars scattered across the night sky. These things feel stable and predictable. Drop an apple and it falls. Turn on a light and it shines. This is the world of everyday experience, the realm of classical physics. But beneath this familiar layer of reality lies a hidden world that is anything but predictable. It is a world where certainty dissolves into probability, where particles can exist in many states at once, and where emptiness is never truly empty. This is the strange and fascinating world of quantum physics, and without it, we cannot hope to understand how the universe could emerge from nothing. The quantum world begins at unimaginably small scales, far below the level of atoms. Atoms themselves, once thought to be indivisible, are composed of even smaller particles. At their core are protons and neutrons, which in turn are made of quarks, tiny entities bound together by a powerful force. Electrons orbit around the nucleus, forming the structure that gives rise to chemistry, molecules, and ultimately life. But these particles are not like tiny billiard balls. They behave more like ripples in invisible fields, appearing as both particles and waves depending on how we observe them. This duality, often called the wave-particle paradox, is one of the most striking features of the quantum world. One of the most important discoveries in this field is the principle of uncertainty, formulated by Werner Heisenberg in the 1920s. It tells us that certain properties, like a particle's exact position and its momentum, cannot both be known at the same time. The more precisely we know one, the less precisely we know the other. At first glance, this sounds like a flaw in our measurements, as though our instruments are not fine enough. But it is not a problem of technol. It is a fundamental truth about reality itself. At the quantum level, nature is not deterministic in the way Isaac Newton once imagined. Instead, it is probabilistic. Particles exist in a cloud of possibilities until an observation forces them into a specific outcome. This idea challenges our deepest intuitions. Imagine tossing a coin. In our everyday world, it is either heads or tails, even before we look. But in the quantum world, a particle is both heads and tails at once, a superposition of states. Only when we observe it does it choose one. This bizarre behavior has been proven again and again in experiments, and it forms the backbone of technologies we use today, from semiconductors to quantum computers. But it also raises profound questions about what reality really is when no one is looking. To investigate the secrets of this hidden world, scientists build some of the most advanced machines ever created, particle accelerators. These colossal devices use electromagnetic fields to speed particles up to nearly the speed of light, then smash them together with incredible energy. When this happens, the collisions briefly recreate the extreme conditions that existed just after the Big Bang. In those fleeting moments, new particles emerge, some predicted by theory, others completely unexpected. These collisions provide us with glimpses into the building blocks of matter and the forces that govern them. One of the most famous accelerators is the Large Hadron Collider, a circular machine buried beneath the border of Switzerland and France. Stretching for 27 kilometers, it is a triumph of human engineering. In 2012, it made history with the discovery of the Higgs boson, a particle that had been predicted decades earlier. The Higgs boson is linked to the Higgs field, an invisible energy field that permeates the universe. Without this field, particles would have no mass. They would never clump together to form atoms, stars, or people. The discovery of the Higgs boson filled a crucial missing piece in our understanding and confirmed that the quantum world shapes reality at the most fundamental level. The framework that ties much of this together is called the Standard Model of Particle Physics. It is one of the most successful scientific theories ever created, explaining how fundamental particles interact through three of the four known forces: electromagnetism, the strong nuclear force, and the weak nuclear force. According to the Standard Model, all matter is built from a handful of fundamental particles: 6 types of quarks, 6 types of leptons, and a set of force-carrying bosons. It is elegant, predictive, and has been confirmed by countless experiments. Yet, for all its power, the Standard Model is incomplete. It leaves gravity unexplained and cannot account for the dark matter and dark energy that make up the vast majority of the universe. This incompleteness is both frustrating and exciting. On one hand, it shows that our current theories cannot give us the full picture of reality. On the other, it points toward new physics, deeper layers of understanding waiting to be discovered. For instance, physicists believe there may be entire families of particles we have not yet detected, perhaps linked to dark matter. Some suggest that new dimensions of space might exist. Beyond the three we see, hidden at scales too small for us to perceive, the quantum world seems to whisper that there is always more than meets the eye. But what does all this have to do with the question of nothingness? In quantum physics, nothing is never truly nothing. Even in a perfect vacuum, particles and antiparticles constantly flicker into existence, borrowing energy from the void before disappearing again. These virtual particles, as they are called, are not directly observable, yet their effects are real. They can shift the energy levels of atoms, bend the paths of other particles, and even exert forces. This restless activity suggests that the vacuum itself contains hidden energy, a kind of quantum potential that may have played a role in the birth of the universe. Some theories propose that the entire cosmos began as a quantum fluctuation, a ripple in this underlying field that expanded and grew into everything we see today. If true, then the origin of the universe was not creation out of absolute nothing, but a transformation of quantum energy into matter and space-time. It is a picture where existence emerges not from a void, but from the quantum uncertainty that refuses to stay empty. The quantum world also hints at connections we do not yet fully grasp. Particles can become entangled, meaning their states are linked even across vast distances. Measure one, and the other instantly reflects the result, no matter how far apart they are. This phenomenon, which Einstein once dismissed as spooky action at a distance, has been demonstrated repeatedly and now forms the basis of new technologies like quantum communication. But it also suggests that the universe may be more deeply interconnected than we ever imagined. As strange as these ideas sound, they are not speculation. They are the results of decades of experiments, theories, and discoveries. Quantum mechanics is not only the foundation of modern physics, it is the engine behind much of our technology: lasers, smartphones, computers, and medical imaging. It is both practical and profoundly mysterious. And yet, despite all we have learned, we are left with an unsettling realization. The more we uncover about the quantum world, the stranger the universe appears. It is as though reality itself is built on rules that defy common sense, rules that hint at an origin story more bizarre than we could ever have imagined. The quantum world teaches us that certainty is an illusion, that emptiness is never truly empty, and that existence itself may be the outcome of fluctuations in an invisible field of energy. As we look deeper, we realize that understanding the quantum realm is not just about knowing how particles behave, it is about discovering the possible pathways from nothing to everything. If the quantum world reveals the building blocks of matter, then the next step in our journey is to understand the rules that govern them. Matter alone is not enough to create a universe. Without forces to pull, push, bind, and shape, the cosmos would remain a chaotic sea of particles drifting without pattern. The universe as we know it exists because there are fundamental interactions, forces of nature, that dictate how particles behave, how structures form, and how reality evolves. They are invisible and yet everywhere, acting across scales as vast as galaxy clusters and as small as the heart of an atom. Physicists recognize 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These 4 forces form the scaffolding of the universe, weaving together everything from the tiniest subatomic particles to the grandest cosmic structures. Without them, there would be no stars, no planets, no chemistry, no life. They are not just rules written into the fabric of reality. They are the very reason reality can exist at all. Gravity is the most familiar of these forces. We feel it every day, keeping our feet on the ground, anchoring the oceans, and guiding the paths of planets around the sun. Isaac Newton described it as a universal attraction between masses. The greater the mass, the stronger the pull. But Newton's view was only part of the story. Centuries later, Albert Einstein revealed that gravity is not a force in the traditional sense, but the bending of space and time itself. Massive objects warp the fabric of space-time, and smaller objects follow the curves of this invisible landscape. The Earth does not so much orbit the Sun as it falls endlessly along the curvature that the Sun's mass creates. Gravity is the weakest of the four forces, yet it dominates the large-scale structure of the universe because it acts over infinite distances. It sculpts galaxies, drives the birth of stars, and binds the cosmos together. Without it, matter would never have coalesced after the Big Bang. The second force, electromagnetism, is far stronger than gravity and is responsible for nearly every interaction we encounter in daily life. It governs the attraction between charged particles, the structure of atoms, the chemistry of molecules, and the very signals that pass through our nervous systems. When you see light, feel the heat of the sun, or use electricity, you are experiencing the effects of electromagnetism. It is mediated by photons, particles of light that carry electromagnetic interactions across space. Electromagnetism has both an attractive and repulsive side. Opposite charges pull together, while like charges repel. This balance makes it possible for atoms to bond, molecules to form, and life to emerge. It is the force behind lightning storms, magnets sticking to your refrigerator, and the very existence of technology. Unlike gravity, electromagnetism can cancel itself out when positive and negative charges balance, which is why on large cosmic scales it seems less dominant than gravity, even though at the particle level it is immensely powerful. The third force is the strong nuclear force, sometimes called the strong interaction. It is the most powerful of the four, but it acts over incredibly short ranges, limited to the size of an atomic nucleus. Without it, atoms would not exist. Inside the nucleus, positively charged protons naturally repel each other, since like charges push apart. If left unchecked, this repulsion would blow the nucleus apart. But the strong force overwhelms this repulsion, gluing protons and neutrons tightly together. This force is mediated by particles called gluons, whose name is fitting. They act as the glue that binds quarks inside protons and neutrons, and then binds those protons and neutrons into atomic nuclei. The strength of this force is astonishing. To break apart the nucleus of an atom requires immense energy, which is why nuclear reactions release such tremendous power. The strong force is responsible for the stability of matter itself, the very reason atoms can endure. Without it, there would be no periodic table, no stars, and no building blocks for life. The fourth force is the weak nuclear force, and while its name suggests fragility, its role is essential to the universe. The weak force is responsible for certain kinds of radioactive decay and for the nuclear reactions that power stars. It can change one type of particle into another, for example, transforming a neutron into a proton, an electron, and a neutrino. In the core of the Sun, the weak force enables hydrogen atoms to fuse into helium, releasing the energy that warms our planet and fuels life. Without the weak force, stars would never shine, and the elements that make up our bodies, carbon, oxygen, iron, would never have been forged in stellar furnaces. Though it acts only at subatomic scales and is weaker than electromagnetism and the strong force, the weak force is indispensable for cosmic evolution. Together, these four forces are like the rules of a grand game. They dictate how matter interacts, how energy flows, and how structures emerge. Their interplay shapes the entire history of the universe, from the formation of the first atoms to the clustering of galaxies billions of years later. And yet, as much as we understand them, there are still mysteries. Why are there exactly four? Why do they have the strengths they do? If the strong force were only slightly weaker, nuclei could not form. If electromagnetism were slightly stronger, atoms as we know them would be unstable. The balance of these forces seems finely tuned, as if the cosmos itself is delicately balanced to allow for complexity and life. Physicists have spent decades trying to unify these forces into a single framework. The Standard Model successfully unites electromagnetism with the weak force into what's known as the electro-weak interaction, and it describes the strong force with extraordinary accuracy. But gravity remains the outlier, stubbornly resisting incorporation. Einstein's general relativity describes it beautifully on large scales, while quantum mechanics rules on the small. Yet the two theories clash when pushed to extremes, such as in the heart of a black hole or the very first moments of the Big Bang. The search for a theory of everything, one that unites all four forces, remains one of the deepest quests in science. String theory, loop quantum gravity, and other bold ideas attempt to bridge this divide, but so far no single theory has triumphed. What is clear is that without these forces, the universe would be unrecognizable. Imagine a cosmos without gravity, no stars, no galaxies, no planets. Imagine a universe without electromagnetism, no light, no chemistry, no life. Without the strong force, atoms would dissolve into chaos. Without the weak force, stars would never shine. These four interactions are the hidden architecture of reality, the invisible threads that weave the tapestry of existence. As we reflect on them, we see that the story of the universe is not only about particles and matter, but about relationships and interactions. The forces are what transform a collection of particles into something greater, a cosmos capable of beauty, structure, and life. They are the reason that the universe is not simply a void of scattered matter, but a living, evolving system. And so as we continue our journey from nothing to everything, we realize that these forces are not just abstract ideas in textbooks. They are the heartbeat of the universe, the reason the stars shine above us, the reason matter holds together, the reason we exist at all. To understand the building blocks of reality, physicists needed more than just a list of particles. They needed a framework, a grand map that could explain how matter and forces fit together. That framework is called the Standard Model of particle physics, and it is one of the most successful scientific theories ever created. It is our best attempt so far at describing the fundamental components of the universe, a kind of periodic table for the cosmos at its deepest level. And yet, despite its incredible success, the Standard Model is not the final answer. It explains much, but leaves many of the biggest mysteries unsolved. The story of the Standard Model begins in the mid-20th century. By then, physicists had already discovered that the atom was not indivisible, but made of smaller parts, a dense nucleus containing protons and neutrons surrounded by electrons. Soon, even protons and neutrons turned out to be made of something smaller still, quarks. As more and more particles were discovered in experiments, scientists needed a way to organize them to make sense of the apparent chaos. The Standard Model emerged as that organizing principle, classifying particles into families, explaining their interactions, and predicting the existence of new particles that were later confirmed. At its core, the Standard Model divides the universe into two kinds of entities: matter particles and force carriers. Matter particles are the building blocks of everything we see around us. They include quarks and leptons. Quarks combine to form protons and neutrons, while leptons include the electron, which orbits the nucleus of atoms, and its ghostly cousins, the neutrinos. These particles make up the matter of stars, planets, and people. Without them, the universe would be an empty void. On the other side are the force carriers, also called bosons. These particles are the messengers of Nature, or these fundamental forces. Photons carry the electromagnetic force, allowing charged particles to interact and giving us light itself. Gluons carry the strong force, binding quarks together inside protons and neutrons. The W and Z bosons carry the weak force, enabling the processes that power the sun and create the heavier elements necessary for life. And then there is the Higgs boson, the particle discovered in 2012, which is linked to the Higgs field. This invisible field fills all of space and gives mass to other particles as they move through it. Without the Higgs mechanism, particles would remain massless, incapable of forming atoms, chemistry, or life. Together, these matter particles and force carriers form the foundation of the Standard Model. The model describes how they interact, how they transform, and how they give rise to the complexity of the universe. It has been tested again and again in experiments, and time after time, its predictions have proven correct. It is a triumph of human ingenuity, a mathematical blueprint of reality. But as powerful as it is, the Standard Model is not perfect. For one, it does not include gravity. Einstein's general relativity describes gravity as the curvature of space-time, not as a force carried by a particle. Yet many physicists believe there must be a particle associated with gravity, sometimes called the graviton. If it exists, it does not fit within the standard model. This gap points to the deeper problem of unifying quantum mechanics, which governs the very small, with relativity, which governs the very large. The two theories work brilliantly in their own domains, but clash at the extremes, such as inside black holes or at the first instant of the Big Bang. Another mystery the standard model cannot explain is dark matter. Astronomical observations show that galaxies rotate in ways that cannot be accounted for by the visible matter we see. Something invisible must be providing extra gravitational pull. This unseen mass, dark matter, makes up about 27% of the universe, yet it does not interact with light, and it is not part of the standard model. Likewise, dark energy, the force driving the accelerated expansion of the universe, accounts for nearly 70% of the cosmos, yet it has no place in the standard model. This means that the particles we know and the forces we have studied account for less than 5% of the total universe. The rest remains hidden, beyond the standard model's reach. Even within the particles, we do know there are puzzles. Neutrinos, for instance, are so light and elusive that billions of them pass through your body every second without leaving a trace. For decades, the standard model treated neutrinos as massless, but experiments have shown that they do have a tiny mass. This discovery forced physicists to rethink parts of the model, and it hints at physics beyond what we currently understand. The Higgs boson itself also raises new questions. Its discovery confirmed the existence of the Higgs field, but the mass of the Higgs boson turned out to be surprisingly low compared to what some theories predicted. This has led to debates about whether the universe is stable in the long run or whether we live in what's called a false vacuum, a precarious state that could one day collapse into something entirely different. While such a collapse would likely take trillions of years, it raises profound questions about the ultimate fate of the cosmos. Despite its limitations, the standard model has revolutionized our understanding of the universe. It has shown us that the apparent complexity of Sagan world reduces to a surprisingly small set of fundamental ingredients. Just as the periodic table organizes the elements into patterns of behavior, the standard model organizes the particles into a coherent framework. It is a reminder that beneath the diversity of reality lies a deep simplicity. The search for physics beyond the standard model continues. Physicists build ever more powerful accelerators, design sensitive detectors buried deep underground, and launch observatories into space, all in the hope of catching a glimpse of new particles or forces. Each discovery could expand the map of reality, revealing new layers of existence. Perhaps there are undiscovered particles that make up dark matter, or new symmetries that unify the forces. Perhaps gravity itself will one day be woven into a grander theory. Whatever the future holds, the standard model is the stepping stone to deeper truths. And yet the very fact that it is incomplete makes it even more powerful. It tells us that the universe is not yet fully explained, that mysteries remain, and that science is an open journey rather than a closed book. The standard model is not the end of the story. It is the beginning of the next chapter. As we continue our exploration of how the universe was born, the standard model gives us the tools to look back in time. It allows us to recreate the conditions of the early universe in particle accelerators, to test how matter and forces behaved in the first fractions of a second after the Big Bang. It bridges the gap between the quantum realm and the cosmos, between the tiniest particles and the vastness of space. And while it cannot yet explain everything, it points the way forward, reminding us that even the smallest particles hold the keys to the largest mysteries. When we ask how the universe began, one answer rises above all others: the Big Bang. It is perhaps the most famous scientific theory in all of cosmology, and for good reason. It tells us that about 13.8 billion years ago, everything we see today, the stars, the galaxies, the space between them, was once concentrated in an unimaginably hot, dense state. Then, in a moment that defies ordinary comprehension, space itself began to expand. This was not an explosion of matter into an empty void. It was the stretching of space and time, the unfolding of the very fabric of reality. From that tiny, blazing beginning, the universe has been expanding and cooling ever since, giving rise to the cosmic structures we now observe. To visualize this, scientists often use the analogy of a balloon. Imagine drawing dots on the surface of a balloon and then inflating it. As the balloon expands, the dots move away from each other. None of the dots is the center of expansion. Instead, the entire surface grows, stretching the distances between every point. Our universe works in a similar way. Galaxies are carried apart not because they are flying through space, but because space itself is expanding. This idea is counterintuitive but powerful. It tells us that the Big Bang was not an explosion into space, but the creation of space itself. The evidence for the Big Bang is compelling, and it comes from multiple directions. One of the strongest pieces of evidence is the redshift of galaxies. In the 1920s, astronomer Edwin Hubble made the groundbreaking discovery that distant galaxies are moving away from us, and the farther away they are, the faster they recede. The light from these galaxies is stretched to longer, redder wavelengths as space expands, a phenomenon known as redshift. This observation shattered the old view of a static universe and revealed that the cosmos is dynamic, constantly evolving. If galaxies are moving apart now, it means they must have been closer together in the past. Rewind far enough, and all of them converge to a single point of origin, the moment of the Big Bang. Another powerful line of evidence comes from the cosmic microwave background radiation, often described as the afterglow of creation. In 1965, two scientists, Arno Penzias and Robert Wilson, were working on a radio antenna when they detected a faint, persistent signal that seemed to come from every direction in the sky. At first, they thought it was interference or even bird droppings inside their antenna. But what they had stumbled upon was something extraordinary. The leftover heat from the early universe, stretched into microwaves by billions of years of cosmic expansion. This radiation, the cosmic microwave background, provides a snapshot of the universe when it was only about 380,000 years old. At that time, the cosmos had cooled enough for electrons to combine with nuclei, forming the first neutral atoms. Light was finally able to travel freely through space, carrying with it a picture of the infant universe. The cosmic microwave background is not perfectly uniform. It contains tiny fluctuations in temperature, variations so small that they differ by only a fraction of a degree. Yet these tiny irregularities were the seeds of everything. Over billions of years, gravity amplified them, pulling matter into clumps that became stars, galaxies, and clusters. In this way, the faint ripples imprinted on the early universe grew into the vast cosmic web we see today. Satellites like COBE, WMAP and Planck have mapped this radiation in exquisite detail, turning the sky into a baby picture of the universe. These observations match the predictions of the Big Bang theory with stunning accuracy. The Big Bang also explains the abundance of light elements in the cosmos. In the first few minutes after the universe began, it was still unimaginably hot, dense, and energetic. In that brief window, nuclear reactions fused protons and neutrons into the first atomic nuclei, mostly hydrogen, helium, and small amounts of lithium. This process, called primordial nucleosynthesis, left behind a chemical fingerprint that we can still see today. Observations of stars and gas clouds confirm that the proportions of these light elements align almost perfectly with what the Big Bang predicts. All of this evidence paints a consistent and compelling picture. The universe truly did begin in a hot, dense state and has been expanding ever since. Yet the Big Bang theory is not without its mysteries. For one, it does not tell us what caused the bang in the first place. It describes how the universe evolved after it began, but remains silent about what came before. Was there truly nothing, or did the Big Bang emerge from a deeper reality we cannot yet see? Some physicists suggest that the universe could have arisen from quantum fluctuations, that the void itself is unstable and capable of producing space and time. Others speculate about cycles of expansion and contraction, with our universe being just one in a series of endless cosmic rebirths. These questions remain at the cutting edge of science and philosophy. Another puzzle is the remarkable uniformity of the universe. When we look at the cosmic microwave background, we see that regions separated by vast distances have almost exactly the same temperature. Yet according to the speed of light, those regions should never have been able to interact with each other in the early universe. How could they have come to such precise agreement? The most widely accepted solution is cosmic inflation, the idea that in the first fraction of a second, after the Big Bang, the universe underwent a period of exponential expansion, stretching tiny quantum fluctuations into large-scale structures. Inflation smooths out the early cosmos, explaining its uniformity, while also planting the seeds of galaxies. Though inflation fits the data well, it remains a hypothesis awaiting direct confirmation. Perhaps the greatest mystery is what lies beyond the Big Bang itself. The very equations of general relativity break down at the singularity, the point of infinite density and temperature at the beginning. Physics as we know it cannot penetrate that boundary. To go further, we need a new theory that unites quantum mechanics with gravity, something like a quantum theory of space-time. Until then, the very first moment of creation remains hidden from us, a veil we cannot yet lift. Despite these unanswered questions, the Big Bang has transformed our understanding of reality. It shows us that the universe is not eternal and unchanging, but dynamic, evolving, and finite in age. It has a history, a timeline that stretches from the first flicker of creation to the galaxies we see today. It has given us a narrative of cosmic evolution, one that connects the smallest particles to the largest structures. Perhaps the most humbling realization is that we are participants in this grand story. The atoms in our bodies were forged in stars, which themselves formed from the elements born in the Big Bang. When we look at the night sky, we are not just gazing at distant lights, we are seeing the unfolding of a 13.8 billion year journey that began in fire and continues in us. The Big Bang is not just a scientific theory, it is the origin story of everything we know. As we continue forward, the Big Bang serves as both a foundation and a frontier. It explains much but not all. It answers some questions while opening new ones. And it reminds us that to understand the universe is not just to study its parts, but to trace its history, to follow the thread of time back to the very moment when nothing became everything. If the Big Bang is the theory that explains how our universe began, then the cosmic microwave background is the photograph that proves it. It is the oldest light we can see, a faint glow that fills the entire sky, stretching across the universe in every direction. It is not the light of stars or galaxies, but something far older, a relic from the time when the universe was still in its infancy. When scientists look at it, they are peering back nearly 14 billion years to a time when the cosmos was less than 400,000 years old. This afterglow of creation, this subtle radiation that whispers from the depths of time, is one of the most compelling pieces of evidence we have that the Big Bang really happened. To understand why the cosmic microwave background is so important, we need to picture the state of the universe shortly after the Big Bang. In those first moments, the cosmos was a blazing soup of energy and particles. Temperatures were so high that atoms could not exist. Protons and electrons were constantly colliding with photons, scattering light in every direction. The universe was opaque, like a dense fog where light could not travel freely. If you could somehow stand inside that early universe, you would see nothing but a brilliant, blinding plasma, light trapped and bouncing endlessly without escape. But the universe was expanding, and as it expanded, it cooled. Eventually, about 380,000 years after the Big Bang, the temperature dropped enough for electrons to combine with protons and form neutral atoms. This event is called recombination, and it changed everything. Once electrons were bound into atoms, light was no longer constantly scattered. For the first time, photons could stream freely across the cosmos. The fog lifted, and the universe became transparent. The light released at that moment has been traveling through space ever since. Over billions of years, as the universe expanded, that light was stretched to longer, cooler wavelengths, shifting from the visible spectrum into microwaves. Today, it arrives on Earth as the cosmic microwave background. The discovery of this ancient radiation was, in a sense, accidental. In 1965, Arno Penzias and Robert Wilson were working at a radio observatory in New Jersey, testing a large antenna originally designed for satellite communication. No matter how they adjusted their equipment, they kept detecting a faint background noise that wouldn't go away. They even went so far as to clean out pigeon droppings from inside the antenna, thinking it might be the source of the problem. But the noise persisted, uniform across the sky day and night. What they had stumbled upon was not interference, but the faint echo of the Big Bang itself. The discovery of the cosmic microwave background confirmed what theorists had predicted, that if the universe began in a hot, dense state, there should still be leftover radiation from that time. At first, this background radiation appeared almost perfectly uniform, the same temperature in every direction. That uniformity is striking. It means that regions of the early universe, separated by vast distances, somehow had the same conditions. But upon closer inspection, scientists found that the radiation is not entirely smooth. It contains tiny fluctuations, minute differences in temperature measured in millionths of a degree. These fluctuations are the seeds of all cosmic structure. Over billions of years, gravity amplified them, pulling matter into denser regions, which grew into stars, galaxies, and clusters. In other words, the slight unevenness of the cosmic microwave background is the reason the universe has structure at all. Without those tiny ripples, everything might have remained a uniform soup of matter and energy, and we would not exist. Modern satellites have mapped the cosmic microwave background in extraordinary detail. In the early 1990s, NASA's COBE satellite measured the first faint fluctuations, showing that the radiation was not perfectly smooth after all. Later missions, such as WMAP and the European Space Agency's Planck satellite, created detailed maps of the sky, revealing a tapestry of hot and cold spots that correspond to density variations in the infant universe. These maps are often called the baby picture of the cosmos because they show us what the universe looked like before stars and galaxies had formed. From them, scientists can extract precise information about the age of the universe, its composition, and its geometry. The cosmic microwave background tells us that the universe is 13.8 billion years old. It tells us that only about 5% of the cosmos is made of ordinary matter, the kind that makes up stars, planets, and people. About 27% is dark matter, invisible and detectable only through its gravitation. All effects. The remaining 68% is dark energy, the mysterious force driving the accelerated expansion of the universe. All of this information is encoded in the patterns of temperature and polarization in the ancient light of the cosmic microwave background. By studying this radiation, we are not just looking back in time, we are uncovering the fundamental ingredients of the universe. One of the most remarkable features of the cosmic microwave background is its near uniformity. How could regions on opposite sides of the sky, too far apart to have exchanged information at the speed of light, have nearly identical temperatures? This puzzle is known as the horizon problem, and it is one of the key motivations behind the idea of cosmic inflation. Inflation proposes that in the first fraction of a second after the Big Bang, the universe expanded at an exponential rate, smoothing out irregularities and creating the uniform conditions we now observe. Tiny quantum fluctuations during inflation were stretched to cosmic scales, imprinting the ripples we see in the microwave background. In this way, the cosmic microwave background is not only evidence of the Big Bang, but also a window into the very earliest moments of the universe. The study of the cosmic microwave background also raises deep philosophical questions. The fact that this ancient light exists at all means that the universe has a knowable history, that we can look back and trace its evolution. It tells us that the cosmos is not eternal and unchanging, but dynamic and finite in age. At the same time, it reveals mysteries we have not yet solved. What exactly is dark matter? What is dark energy? What triggered inflation? And what, if anything, came before the Big Bang? These are questions that the cosmic microwave background cannot fully answer, but it guides us toward them. It is both a revelation and a reminder of how much we still do not know. For us on Earth, the cosmic microwave background is invisible to our eyes, but it surrounds us at all times, washing over our planet from every direction. Every time you turn on an old television and see static on the screen, a small fraction of that noise is actually the faint signal of the Big Bang's afterglow. We are literally immersed in the light of creation, even if we rarely notice it. Perhaps the most humbling aspect of the cosmic microwave background is what it tells us about our place in the universe. Those faint ripples in the ancient radiation are the direct ancestors of galaxies, stars, and planets. Without them, we would not exist. The atoms in our bodies, forged in stars billions of years later, owe their existence to the tiny fluctuations in a glow of light released almost 14 billion years ago. When we study the cosmic microwave background, we are studying the origins not just of the cosmos, but of ourselves. The cosmic microwave background is a cosmic memory, a frozen imprint of the universe's childhood. It connects us to the very beginning, offering a window into a time when the cosmos was young, hot, and full of potential. It is the oldest light, the faint whisper of an event that turned nothing into everything. And as we look into that ancient glow, we realize that we are part of the story it tells, a story written in light, carried across billions of years, waiting for us to discover. In the earliest moments after the Big Bang, the universe was a place of extremes. Time itself had barely begun, and the entire cosmos was smaller than an atom, hotter than the core of a star, and denser than anything we can imagine. At that scale, the familiar rules of physics break down, and the strange laws of quantum mechanics dominate. In this quantum realm, uncertainty is not just a feature of measurement, it is a fundamental part of reality. Even what we see, our empty space is never truly empty. It seethes with energy, with particles flickering into and out of existence in fleeting bursts known as quantum fluctuations. These fluctuations, tiny ripples in the vacuum, may seem insignificant, but they hold the key to understanding why the universe looks the way it does. In the first fraction of a second after the Big Bang, cosmologists believe the universe underwent a phase of rapid, exponential expansion called cosmic inflation. During this period, space itself stretched at an astonishing rate, growing from subatomic scales to macroscopic size in the blink of an eye. Inflation smoothed out irregularities, explaining why the universe appears so uniform on large scales. But it also magnified those tiny quantum fluctuations, stretching them into cosmic seeds. Those minuscule ripples in density became the scaffolding for everything that would follow: the galaxies, stars, planets, and life itself. Without the quantum uncertainty built into nature, the universe might have remained a featureless expanse of energy with no structure at all. As inflation slowed and the universe continued to expand, it began to cool. Within the first microsecond, quarks and gluons condensed out of the primordial plasma, binding together to form protons and neutrons. This was the first step toward matter as we know it. A few minutes later, as the temperature dropped further, these particles fused into the nuclei of the lightest elements, mostly hydrogen and helium, with traces of lithium. This brief window of nuclear creation is known as primordial nucleosynthesis. The ratios of these elements, still observed today in stars and gas clouds, match the predictions of Big Bang theory with striking precision. Yet the universe was still far from familiar. It was filled with a hot, dense fog of particles and radiation. Atoms as we know them could not yet exist. For hundreds of thousands of years, photons, the particles of light, were trapped, scattering endlessly off free electrons. Only when the universe cooled enough for electrons to bind with nuclei, forming neutral atoms, did the fog lift. Light could finally travel freely, releasing the cosmic microwave background, the ancient afterglow we see today. With atoms now stable, gravity could begin its slow, patient work of gathering matter into clumps. Over millions of years, gas clouds collapsed to form the first stars, and those stars forged heavier elements in their cores. When they died in spectacular supernovae, they seeded the cosmos with the raw materials for planets and life. In this way, the birth of matter set the stage for the universe we inhabit. But as remarkable as this story is, it leaves us with a profound mystery. The universe we see, made of stars, galaxies, planets, and people, accounts for less than 5% of the total cosmos. The rest is hidden from us, invisible and enigmatic. Astronomers discovered this by watching how galaxies move. The stars within them orbit so quickly that the visible matter alone cannot explain the gravitational pull holding them together. Something unseen must provide the extra gravity, something that does not emit or absorb light. This invisible substance is called dark matter. It makes up about 27% of the universe, forming vast halos around galaxies and shaping the large-scale structure of the cosmos. Without dark matter, galaxies would fly apart, unable to hold themselves together. It is the silent scaffolding of the universe, unseen but essential. And beyond even that lies something stranger still: dark energy. In the late 1990s, astronomers studying distant Day supernova made a shocking discovery. Instead of slowing down as gravity should cause, the expansion of the universe is accelerating. Some mysterious force is pushing space itself apart, driving galaxies away from each other faster and faster. This force, which makes up about 68% of the universe, has been named dark energy. We do not know what it is. It could be a property of space itself, an energy inherent in the vacuum. It could be a sign of new physics, something beyond our current theories. Whatever it is, dark energy dominates the fate of the cosmos, determining whether the universe will expand forever, tear itself apart, or one day collapse back into nothingness. Together, dark matter and dark energy account for 95% of reality, yet they remain invisible to our instruments, detectable only through their effects. This means that everything we have ever seen, every star, every galaxy, every living thing, makes up only a tiny fraction of the whole. The vast majority of the universe is hidden, a cosmic mystery waiting to be solved. And so the story of the universe is both astonishing and incomplete. From quantum fluctuations to cosmic inflation, from the birth of matter to the rise of galaxies, we can trace the journey from nothing to everything. But when we ask what most of the universe is actually made of, the answer remains elusive. Dark matter and dark energy are placeholders, names for puzzles we have not yet solved. They remind us that our understanding is still a work in progress, that the universe is far stranger and richer than we can imagine. The last 3 chapters of this story reveal both our triumph and our humility. We have uncovered how quantum ripples became galaxies, how the first particles became stars, and how hidden forces continue to shape the cosmos. Yet the majority of existence remains in shadow. The search for answers continues in underground detectors, in space telescopes, in the equations of theoretical physics. Each step brings us closer, but each discovery also opens new questions. And perhaps that is the greatest wonder of all, that the universe is not a solved puzzle, but an unfolding mystery, inviting us to explore. From the first flicker of existence to the vast expanse of galaxies, our journey through the universe has brought us face to face with some of the deepest mysteries of reality. We began with nothingness, or what we thought was nothingness, and discovered that even emptiness is alive with possibility. Quantum fluctuations, uncertainty, and hidden energies all remind us that nothing may be far stranger than something. From that restless void, space and time unfolded, the laws of physics took shape, and the universe began its grand story. We watched as inflation stretched the tiniest ripples into cosmic structures, as particles condensed into protons and neutrons, and as the first atoms were born. The glow of the cosmic microwave background still carries the memory of that early fire, whispering to us across billions of years. Gravity gathered clouds of hydrogen, stars ignited, and within those fiery furnaces, the elements of life were forged. In the death of stars came rebirth, new worlds seeded with carbon, oxygen, and iron, the very atoms in our blood and bones. The universe is not only out there, it is in us. Along the way, we discovered 4 invisible forces that guide the cosmic dance: gravity binding galaxies, electromagnetism shaping chemistry, the strong nuclear force holding atoms together, and the weak force powering the stars. We explored the standard model of particle physics, a near-complete map of matter and forces. It explained so much, but not everything. Gravity stood apart, dark matter and dark energy remained in the shadows, and the dream of a theory of everything still beckoned. And so we arrive at the present, a universe 13.8 billion years old, still expanding, still evolving. Yet even now, we stand in the midst of mystery. What is dark matter? What is dark energy? Why do the laws of physics take the form they do? And perhaps the greatest question of all, why is there something rather than nothing? Science has given us profound answers, but also deeper questions. The story of the universe is not finished, it is ongoing. Every discovery opens a new door. Telescopes peer deeper into space, particle accelerators probe the smallest scales, and theories attempt to weave gravity into the quantum world. Each step brings us closer, but each step also shows us how vast the unknown truly is. Yet perhaps that is the beauty of it. The universe is not a puzzle with a final piece, but a story that keeps unfolding. And we, small creatures on a pale blue dot, are part of that story. The atoms that make us were born in ancient stars. The thoughts in our minds are shaped by the same laws that govern galaxies. We are the universe, looking back at itself, asking questions only it could ask. As we close this journey, let us remember, from nothing came everything, and from everything came us. The next chapters of this story are still being written by scientists, thinkers, dreamers, and by you. The universe is not just out there, it lives in your curiosity, your imagination, and your wonder. If this journey has sparked your curiosity, don't let it end here. Like, share, and subscribe to join us as we continue exploring the mysteries of existence. Together, we'll keep asking the greatest question of all: how did nothing become everything?